How do we find inverses? The process is theoretically simple enough, although it can not be sort of tricky to actually do it. Let's present that material. So for starters, let's ignore function notation. Let's say you have y equals 1 divided by x plus 2. And we're not using function notation here, but we could certainly think of this as a function that takes x as its input and gives y as its output. And what we want is to undo that. We want to take y as our input and get x as our output. Can we manage that? Well, let's perform some algebra on this equation. And I'm not going to provide a lot of motivation for this algebra at the moment. I'm just going to do it, but we could subtract 2 from both sides if we wanted to. And we could multiply both sides by x if we wanted to. And then we could divide both sides by y minus 2 if we wanted to. And what do we have here? Well, now we can plug y into this and get x out. This is exactly what we were looking for. So, to find an inverse, we abandon function notation. We write y equals something involving x. And then we solve to get x equals something involving y. And then there's going to be a last step, which will explain when we do it, which I'm going to call switching the variables. Let's tear that out so we can refer back to it as needed. And that's that f of x be 1 divided by 2x plus 3. And let's find f inverse of x. Now we know that not all functions are invertible, Presumably, if I'm asking you to find an inverse, it's because that inverse exists. If we take a look at Desmos.com and the graph of this function, it does pass the horizontal line test. Any of these horizontal lines only touch the red curve once. It may kind of look like the horizontal line at 0 will touch the curve more than once, maybe somewhere out here, and then again somewhere out here. Actually, the horizontal line at 0 misses the curve entirely, doesn't touch it at all. So, we'll follow these steps that I've laid out. We are not going to use function notation until the very end. Let's write y equals 1 divided by 2x plus 3. And now this becomes an algebra exercise. We need to solve for x. So x is in the denominator of a fraction. If we want to solve for x, we need it to not be in that denominator. So probably the first thing we should do is multiply both sides by this. Now we want x by itself on the left and our y's over on the right. So maybe the next thing we should do is get that y over here. We can do that if we divide both sides by y. Subtract 3 from both sides. And finally, divide both sides by 2. I'm going to rewrite this slightly. If you have a difference divided by 2, that's 1 divided by y divided by 2 minus 3 divided by 2. So here, more or less, is our inverse. What's up with this last step? Well, if we now wrote this in function notation, we'd write, let's call it g. G of y equals 1 divided by 2y minus 3 halves. That's fine as far as it goes, but f inverse should have the same variable as the original function, x here, x x here. It shouldn't have y as its variable. So all that this last step does is switch our variables so that we can write f inverse of x. And the reason we can get away with this is that it doesn't matter fundamentally what you call your variable. I mean, what are we doing here? We're multiplying our variable by 2. We're putting it in the denominator of this fraction, and then we're subtracting 3 halves. So I was able to describe what this function does without saying what the variable is named. Whether we call the variable y, whether we call the variable x, whether we call the variable t, it's still the same function. So we can rename our variables like this if we wish to.